So today we're going to review and do some new things with electric fields. And I'm going to remind you that a field is simply an association of a physical quantity with a location in space. And we always calculate fields at a location in space. That's what they are. And electric fields are, we'll talk a little bit more about this, the force per unit charge. Once we've done talking about some E-fields, we'll talk about some maps, we'll talk about how to do some calculations, and we'll maybe get to, but probably not, computing E-fields from continuous charge distributions. So remember, a field is the association of some physical quantity in space, and we calculate it at a location in space. So here's a little diagram of what an electric field is. We think about taking a positive test charge. We place it at some point, x, y, z. That's where we want to find the field. We're going to sample the space. We put that QT down, and we look at the force, and we measure the force. The electric field is defined as the force we measure divided by the test charge. The test charge is always positive. That's the definition. So we have the idea that we can sample or test and find the electric field F over QT at any point in space. And we measure at points in space using this kind of technique. Okay, so one of the things that we can do is we can make a map of a field. So a map of a field is just a sort of spatial or pictorial representation of what the field looks like. We think about what would happen if we put a positive test charge all around all kinds of places in space. So the common place to start is with a positive single point charge. So in the left, you see a positive charge. And if we thought about dropping a positive point charge, a test charge, at all of these locations around that positive charge, Q on the left, well, that positive test charge would always be repelled by that plus. So everywhere it would experience a force away. So we can draw the forces and the field, which is the force divided by the charge, and we see that it's always repulsive. So we can draw fields like this, just kind of pictorially representing them. There are a few simple rules. Field lines always start on positive charges. They end on negative charges. They never cross. And field lines always look like they repel each other. So let's look at another example. Let's look at a minus charge. So for a negative charge, a positive test charge would always be attracted to it. So those field lines go inward. They end on that negative charge. And that's one of our rules, that field lines end on negative charges. We can draw something called an electric dipole, a plus-minus pair separated by some distance. And you can see that if you put a positive test charge in between them, it will be repelled by the plus and attracted by the minus. And in fact, in general, it shows that behavior. Notice how these field lines look like they're kind of blown out and repelling each other. Again, one of the examples of how we draw these. Now, these are really sketches, right? They're not really calculations. Here's an example of two positive test charges. So we see the field lines again looking like they're repelling each other. Now, if you thought about putting a positive test charge exactly in the middle of those two, you'd find that you could find a spot where there is no force. The forces would be exactly balanced, downward from the top charge, upward from the bottom charge. So there's this spot in the middle where there aren't any field lines, and that's because, well, there aren't any fields. Notice how the field lines are kind of repelling each other. And again, these are really kind of sketches. They're not high precision diagrams. They're just giving you a sense of what happens. How does it work? It's pretty fun to do this. They can get out of hand quickly if you have too many charges, but you can draw pretty complicated drawings. Now, ultimately, you want to calculate. So imagine we had a charge, a plus charge at the origin, and we put a QT, and you can see the QT there, at some distance away. So the magnitude of the electric field would be the force over the QT. The force we know from Coulomb's law, QT over 4 pi epsilon naught r squared divided by QT. So the electric field due to a positive test charge is really just this Q over 4 pi epsilon naught r squared. That's the magnitude. And the distance is r, the r vector is present, and r magnitude is present, and the r unit vector is present. So here's the r vector, and it goes from the charge to the point of interest where you're calculating the field. Here's the r hat in the same direction. And so, the electric field for a point charge is pretty simple. It looks a lot like Coulomb's law. Now, if you make it more general, let's say you had a charge Q1 at x1, y1, z1, and you wanted to find the field at x2, y2, z2, as we highlight here. Well, then you'd have to figure out that r vector and that r unit vector. And we did this before, right? It's endpoint minus starting point. So x2 minus x1i, y2 minus y1j, z2 minus z1k. And then the magnitude is the square root of the sum of the squares, and the unit vector is r vector over r. So you have to put all that back into that E expression, and voila. Now, you can do it for more than one charge in Q1 and Q2 at these locations. So let's say you want to calculate the field at that point right there, AB. Well, there's a field due to 2 and a field due to 1. So we can write them out separately. So that E2 is Q2 over 4 pi epsilon naught B squared J. It's upward in the J direction. And then E1 has an angle theta associated with it. So we could find the cosine and the sine, and we could then find the magnitude, Q1 over 4 pi epsilon naught times the hypotenuse. And then we could put in all the sines and cosines, write the vector component, and then come out with the full field, which we add up at the left. You could probably do this more easily if you just found the tangent if you knew the numbers. That's a good place for us to stop.